I'm Rad Sommer. Thanks to Milo for giving me this opportunity to speak with you, share my career as an engineer, and let's dive into it here. I grew up on a farm near Spokane, Washington, and I went to a grade school, a very small school. There was only 6 kids in my class. We had 2 classes, 4th and 5th, for instance, in the same grade, in the same room in the school. And so I went through grade school, then into high school, and figured I'd just go on to college. I wasn't sure I wanted to or not, but my dad was interested in me doing that. And so I thought, well, I'll take the SATs and at least see if I can get in. And after I did the SATs, I went to the advisor, the high school advisor, and he helped me fill out the forms to apply. And I had applied to University of Washington, WSU, and then Whitman, but he said there's no chance I could get into Whitman, so we didn't bother. But a few weeks, maybe a month later, I got a mail from Whitman saying they got my SATs, but they never got my application. So I took that to my advisor, and I didn't smirk or anything, but I thought it was a little bit, it shows how much chance is involved in a career, because I could have just gone somewhere else and had a totally different life. The other thing is that in high school, I did all right. You know, I took math and physics and chemistry and what have you, and did okay. I didn't study really hard, but a lot of kids didn't, so I did all right. And the main thing, though, is out on the prairie where I lived, nobody went to college, or the ones that did either hated it and quit, or they flunked out. So I was pretty scared when I went to Whitman. When I went there, they had a orientation where you sign up and do your classes. And so the person helping me asked me what I was interested in. And I said, well, I was thinking I was interested in sports and I was interested in girls, but I told him I was interested in drag racing. So he said, well, that's mechanical engineering. So I said, okay. And so I signed up for the classes for that. And all the engineering classes are pretty much the same when you're starting out. But Whitman was in Walla Walla, Washington. It is in Walla Walla, Washington, and it's a really small school. At the time, it was 1,200 students, and my high school was almost 4,000 students. So, and Walla Walla is a town that's still fairly small. I'd, you know, maybe compare it to Healdsburg or something like that. You know, it's not a metropolitan for sure. After the signing up for the classes, I went to an orientation lunch, and there's tables of 4, so people just, you know, incoming freshmen just randomly sat down, and 4 to a table, and the person giving the introduction or moderating said, of the 4 people look around you, 3 of you are not going to graduate. And that was kind of the attitude at that time. It's changed now. Whitman's was then and is now a really great school, but it was way too hard. They tried to make it harder than it needed to be, I thought. So, for instance, I took physics and calculus at the same time. Now most kids have had calculus before they get to college, but at that time it didn't. So trying to learn physics, which relied on calculus, and I didn't know the calculus, was really difficult. And in addition, in freshman physics, there was all the juniors that were in pre-med. You know, they had to take physics it was a requisite for that. So it was difficult, and so I had to really learn how to study. So at the time, Whitman was going through the same sorts of things that everywhere was. In other words, the dominant theme was the Vietnam War, civil rights movement. It was a difficult time, somewhat similar to now, different than before, but you know, we're seeing some of that same stuff. And another thing that factored into it was kids were getting drafted, and they were getting drafted based on where they were in their class. So you had to be above the median to basically not go to Vietnam. And that put a lot of, you know, where a lot of pranks and parties and fun stuff was happening previously, it was less so now. I mean, it was still fun and good times and what have you, but it was a serious time. So, but I really liked that school, and I'm still in a lot of, you know, I have good friends from there. We stay in contact. So small school, small town, but knew people well, et cetera, et cetera. Because they didn't have an engineering school, they just had math physics, I transferred to Columbia in New York City. And it was also a great school, but almost the opposite in every way. It was, you know, I don't know what it was at that time, 8 to 10 million people. It was, you know, the campus was bigger than just the quad near there was bigger than the whole Whitman campus. But it was 30,000 students. There was a graduate school. But it was New York City, and that was also different in that I was living right off Broadway. It was really noisy. It was kind of dangerous at night. But, you know, Greenwich Village, Central Park, the Rockefeller Center, Guggenheim Museums. I mean, it was really exciting, interesting place. If I'd had more time, I would have done more. But at any rate, I got an MSCE there and got an electrical engineering honorary. The reason I got into electrical engineering rather than mechanical engineering was when I was in about 4th or 5th grade, I made a crystal radio set, which was like rolling copper wire around a toilet paper tube and putting a metal strip on it. And I had headsets like this, a little bit clunkier at that time. And then I had to string some baling wire across 2 trees, you know, a dipole antenna. But when I plugged that thing in and it worked, it was like magic, you know, and I was just listening to the radio almost every morning before I got up and went to school. So that kind of stuck in my mind. And I had a job in Spokane during the summers working at a television station, and that was really interesting as well. So I got a ham radio license, and that just pushed me toward electrical engineering. And so that's what I did at Columbia. And but again, it was big, and it wasn't the attitude of make it too hard. I had a friend that was a mechanical engineering student, and one of the hardcore courses of ME is to be thermodynamics. So he took it his junior year and he failed it, or he was going to fail it and dropped out. So he took it as a senior, and he was like halfway through the course and he was failing again. He went to his advisor, and his advisor looked at it and said, you know, you've done really well in other classes, and this is going to be a mental block for you, so I'm going to just waive it. So he was able to graduate. You know, it was just a different attitude. But again, both really schools. I learned a lot at Columbia. And another difference was when I graduated, I didn't go to my graduation ceremony. It was going to cost me like $50 to get a cap and gown, and my parents weren't there. I had no friends there. The ceremony consisted of the whole electrical engineering class stood up, they gave a big applause, and then they sat down. So I watched it from while I was eating a sandwich from the science building. So from there, I applied to graduate school, but decided, well, the big thing is I met my wife there, who was also going to Columbia, and we got married in New York City. And she'd lived in San Francisco, and that was Silicon Valley. So I said, okay, let's go. And so we moved to San Francisco. That was that was quite a contrast from New York City. And where there had been a boom in engineering, now there was a bust. It was a aerospace downturn, and I couldn't get a job. So it was really depressing in that sense. But you know, newly married, San Francisco, the hate, you know, Golden Gate Park, North Beach, Chinatown. I mean, it was, and it seemed clean and small after New York City, and reasonably cheap. So I had a apartment. We had an apartment overlooking to see the Golden Gate Bridge and the Bay Bridge. At night it was gorgeous, and it cost us $125 a month. So different times. So I went to, Marilyn got a job right away. She got a job because she knew secretarial skills. And one of her assignments was the telephone company. And long story short, she told them that they should hire her husband. And I got an interview and was hired in. And so I went to work for the phone company, which is a really good experience because it was a huge company. You know, I mean, it's very well disciplined, and all the things about a big company that are big, good and bad. A lot of it was union, which is good and bad. And it was, the hardest part for me was that it was all the engineering, what I would call engineering or design engineering, development engineering, was done at Bell Labs. And so when you got out to the operating companies like Pacific Bell, the kinds of things that I wanted to do were harder to come by. But I remember my first day there, I walked in and I was in the chief engineer's office and introduced around, and I went to sit down, and this guy came up to me and he said, "Hi, I'm radar." And I said to him, "Hi, I'm transmission," because that's the group I was working with. It turned out his name was Radar. So it was a little bit embarrassing. And the first time I went out in the field, I was going with the senior engineer, and we were looking around for the central office in Oakland. And I saw this building. He was driving and I was scouting, and I was looking around, and I saw this really tall building. We're trying to find it. And I said, is it the one with the big speakers on it? And it was microwave antennas. And so that was a little bit embarrassing. But anyway, after the telephone company, I went to work for down in Silicon Valley. We'd bought property here in Sonoma County and were planning to move here, but I couldn't find any work in Santa Rosa or Sonoma County. So I got a job at Varian Associates in Palo Alto, and that was a really excellent job as well. So I learned a lot of things besides electrical engineering. I learned mechanical engineering, high voltage testing, microwave testing, plating, step brazing, electron beam generation. Yeah, really interesting. It was a hands-on company in the sense that I would do my own testing. They had a formal test station, and I went and would use it. But one time I was working there, and there's 20,000 volts on a klystron tube, which is the tube I was responsible for. And, you know, carelessly I touched the cathode and took that 20,000 volts, and it scared me. You know, I thought I was dead. And then when I realized I wasn't, I looked around, because that kind of thing can get you fired at a company like that in those days. So I was trying to play it cool. And I looked at the lead tester, and she kind of looked away. And I don't know to this day, but I think she knew that I'd gotten zapped and was going to pretend like I didn't, because yeah, if I'd have gotten written up, I would have probably been let go. I don't know. So at any rate, from there, we eventually finished our house in Sonoma County, and we moved here right near Freestone. You know, my son went to Apple Blossom School in Twin Hills, and I worked for a company called National Controls, which did electronic weighing. And I worked on a thing called a moment-free load cell, which is it's a transducer that changes force or stress into voltage. And I actually got my first patent making what they call a moment-free load cell, which is a cell that you can put the weight anywhere on a platter and it'll weigh the same. You know, for instance, if you put, you know, your bologna on the top right part of the scale, you don't want it to read differently than if it's in the middle of the scale. So this load cell accomplished that. And then it was combined by other engineers at the company that did the microprocessor, very first introduction to electronic weighing with the microprocessor. So that company, yeah, it was the first chance I had to face this problem that a lot of engineers face as their career goes along. Of I had developed the load cell part of it from just me working on a picnic table with a voltmeter and, you know, whatever I could find, into a division that had 30 people, technicians, engineers, etc. And I couldn't do both the technical lead and the management. So I had to split. I had to make that choice at that point. And I chose to go to the technical way, which I've done a couple of times. So the company grew and it merged and eventually was acquired and ended up moving to the Midwest. So I went to work for a company in Katati called Rheodyne. And that was a really great company as well. It was a lot of fun, and they made injector valves for liquid chromatography. I know one of your other speakers talked about HPLC, but I'll skip that for now. And so I learned programming there. I'd learned Fortran at Columbia, but I learned C programming, and it was a small, fun company to work with, but and they were very profitable, but pretty limited opportunity for electrical engineer. And so I was recruited by BioSearch, which was another biotech company, and there was amazing. I mean, they worked on these DNA or peptide sequencers or synthesizers. So you tear apart, you know, amino acid by amino acid. You took them apart or put them back together, and I developed the microprocessor controller board for that, memory, microprocessor, etc. And that company, one of the first synthesizers was acquired by this company called Cetus, and Kerry Mullis, one of the engineers there, used that to develop PCR, which is what's used, the main thing that's used for this COVID-19 testing now, polymerase chain reaction. And for that, he got the Nobel Prize in 1993. So it was kind of fun to work on an instrument that he'd, you know, actually improved the instrument that he'd used to do that with. So they were acquired by a company called Waters and moved to the Boston area. So I moved on to optical coating, which most of you know about, or at least knew about before. They've since become JDSU, and now it's called Viave, but it's Ockley was yeah. They and JDSU and HP were the, you know, premier companies in Sonoma County, tech companies in Sonoma County, and still are. So there I did, I worked on this thing called the AXAF, which was an X-ray telescope, which followed up the Hubble. I was lead engineer on that. It was a really interesting project. And I worked on spectrophotometers and fiber optic components and MEMS devices, you know, a lot of stuff that's in the optics world. And a couple principals left that place and started up a little startup. And so I joined them. It's called Sierra Photonics up by the airport. And that's where I still am, although it's gone through 3 or 4 different names. You know, it boomed and busted and merged and was acquired and what have you. So there I was doing optical filters and fiber optics components. And one highlight was one of the multiplexers that I developed was selected for best of show at the big design show in San Francisco. So the optical fiber conference. From there, the company eventually was bought out by a company called 26. They're out of Saxonburg, Pennsylvania. And I was engineering manager there for a while, doing design engineering, managing, but recently I moved into a department of one, which is me. It's doing R&D, and it's current projects I'm working on are 2D materials, which some of you may have heard of, mainly graphene to make voltage tunable modulators, and also some magneto-optic stuff. So that's pretty much it.
Okay, Rad, we have a question from Jake, and he is asking, how did the internals of the radio that you built work?
The little crystal radio that I worked on, so the key part of, at the time, I knew it was magic how it worked, and I knew the main components, which is the source, the antenna, and the guts of it, the electronics, and then the headset, which was the receiver. And that's the design of almost everything electrical or optical component-wise to this day. But how the actual guts worked at the time, I had no idea. Now I can tell you that what there was is this little cat whisker that you poked around on a crystal, and the crystal was selenide, which later would be germanium, for those of you that about transistors. So it makes a diode, and it takes radio frequency, which comes out of the air, and demodulates it into audio frequency. And to really go into how that actually works, that would be a lecture in itself. So I hope that answers it.
And Stefan is wondering, how has electrical engineering helped ocean and coastal health? And what projects have you worked on to help marine science? Now, you may answer this.
Yeah, that's a
second part of your talk.
That's a perfect question for the second half of my talk. But I'll give you a brief heads up on it, which is, at first blush when I went out there, there was no connection, meaning it was just out there, and it was really interesting. And but as I got there, I learned there's a lot of overlap. So I know nothing, or very little. I know more now, but I know very little about biology or about marine science. But I know a lot about optics and photonics, and the people out there are brilliant scientists and marine biologists, and they know not so much about optics or light or sensors or that sort of thing. So there's a few things where that overlaps, and I'll cover it in the next half.
Carrie is wondering, what was the favorite project that you've worked on? And what about the most difficult?
Oh, really good question. Probably there's several, but probably the most interesting one I worked on was optical amplifier, which is, so you're probably familiar with an audio amplifier where you talk quietly and it goes into a microphone, and then you have an amplifier that makes that really loud. I mean, in extreme cases, you could make your little, voice level talk, amplify into an entire stadium, at a rock concert or something like that. Optically, it's way different. There's, you're dealing with photons, you're dealing with light. And so how do you make light bigger? And so I actually got a patent on a way to do that. And it was really difficult to do, and really interesting. Yeah. And again, I don't want to be ducking these questions, but to tell you how an optical amplifier works, that'd be a course, not even just a lecture.
Well, we're hoping to have you back in the spring to talk more about optics. But Aaliyah asks, what changes have you seen in optical devices over time? Have they been drastic or slowly modernizing?
Drastic. The principles are a lot the same, back to Maxwell's equations and what have you, 1900s, 1850s, that sort of thing, Faraday rotation, etc. But the things that I'm working on now didn't exist, and some of the materials, although they existed, were not known, you know. So optical devices, so the very first job, I didn't have a computer, you know. There was no such thing as a cell phone. There was um, um, optic, there was no fiber optics. You know, there was fiber optics in the sense that they developed fiber and a few people knew about it at Bell Labs or Lucent or something like that. But fiber optic wasn't in the vocabulary. So all these devices like switches and amplifiers and modulators, demodulators, all that optically just didn't exist. The biggest change, the one that I kind of was prior to and then grew up with and am now involved in, is lasers. You know, how lasers worked, and there was nobody had even heard of them when I was in graduate school, and it was just starting to be a thing when yeah, these companies like optical coating were formed and what have you. So one answer would be the biggest change is lasers.
Stefan asks, what is the most well-known piece of equipment you've worked on?
So the way a cell phone works is it transmits through the air to a cell phone tower. And from the cell phone tower, it's transmitted along fiber to a central office or to a place where they have all these cell towers routed to. And working on the photonic devices that enable that to happen, you know, what they call line modules, amplifiers, detectors, that would be the most significant that I'd worked on.
Okay, I think we're ready for the next part of the presentation.
That's the companies I worked for and sort of the part that I did. Here's the Rheodyne valve briefly. Here's an optical bench where I work. Yeah, part of that's equipment that I didn't build it, but I assembled it and used it. And again, it'd be a real interesting to talk just how that thing works. Here's a couple patents that I have that I was mentioning about tunable filters and modulators. Now we're to the Q&A that we just had, so we'll go on to the Marine Lab. So I work out at the Bodega Marine Lab, and let me just show you where that is. There's an aerial map of it. Can you see my cursor? Here's Bodega Bay. Well, here's the bay, but here's the town of Bodega Bay. Here's the east side. Here's the head. Here's what they call Horseshoe Cove. And right here, you can barely see it, is the Bodega Marine Lab. And here's an aerial view of it looking from the ocean. So here's the south wing, the west wing, and the north wing, and then some dive tanks. And here's the greenhouse that I'll show you later. And here's some trailers. And I actually have a setup in this little trailer here now, which is kind of it's not mine, but I mean, that I have use of that space. So here's another view of it. You can see the bay in the background there. It's the ocean. Here's some of the equipment. So here's the Fluorescence Imaging Lab. That's a fluorescent microscope on the left there, and I'll talk about that a little bit later. Here's some tanks. You know, I work with the Aquatics Resources Group, and they provide all kinds of equipment and support for graduate students and staff and all the people that are working out at the lab there. So some of the things I do there are like eelgrass surveys, and I've done fish surveys, but mostly what I do is when the students do those sorts of things, they drop their nets off at the end of the day, and I and others in the group pick up the nets and take them down and hose them off with fresh water and hang them up to dry and then put them away later. When they need some tanks, you know, we clean the tanks and set them up for what they need, et cetera. So feed fish, that sort of thing. I started doing that sort of thing, and still do that. Here's the wet lab where some of the experiments are made. Here's the greenhouse that I talked to you about. Here's some signaling. So this is some radar and sonar and even atmospheric devices that are out there. Here's the one on the left is a fish survey. So you'll see they're dragging a net through, and they'll count the amount of various species of fish in that. And on the right is a eelgrass survey. So you can see that little quadrant that's there. And so what I would do would be on the dock and giving them the coordinates for the point, and then the diver there goes down and counts the amount of eelgrass in that particular location. This survey was done because they were going to do some dredging, and they wanted to know the effect of the dredging, and the environmental agency required that there be a survey before and after the thing. And another thing I started doing was water quality monitoring. So these are some of the probes I used and some of the instruments I used, and that's me up on what they call the clarifier, taking measurements. So it was a little bit haphazard there, hit and miss, and somebody would need to know what it was. So again, being an engineer and a little bit of discipline in what I did, I started doing it methodically, meaning I would do it once a week, and I would take recordings and keep the data and plot it in a spreadsheet, etc. So that's the data I would take. And one of the next things I started doing was this algae growth. And one of the main thing they use for food for things like oysters, any bivalves actually, is this sea isocrisis. And it's a really interesting, well, I don't know how interested anybody would be in algae. That tells you how far I've gone, because I'm interested in it now. And it's it photosynthesizes. It's a single cell, what they call phytoplankton. So meaning it absorbs energy as opposed to plankton that eat other plankton. So zooplankton that'll eat phytoplankton. Again, it's a lot of jargon and stuff I didn't even know, but it's really, really interesting stuff. So, and the people at the lab are great. They really, anybody will answer questions for you, and anybody will, you know, I've never been told, you know, you're not in your right place or anything like that. It's really, yeah, it's good people, and they're doing good stuff. So here's the isocrisis, how it's made. It's the these flasks have starter algae in them, and then you put them in bigger flasks as they grow, and then you put them in these big tanks over here. Where's my cursor? You see these big tanks, and then they grow until it's, you know, too much phytoplankton in there, and then they move to these big tanks here. And these are really important because they feed all the animals at the marine lab. And if you spike one of these tanks, it's serious. So there, you can only see this one, but there's actually 3 of them. And there's one guy out there that's like hatchery whisperer or something. He can do it better than anybody, and he's taught me a lot about it. So one thing people do, because they're afraid they're going to kill everything, they come in and wipe everything down with iodine, and sure enough, they'll kill a tank. Or they won't do that, and they're kind of sloppy, and they use instruments that they've used before, etc., and they you know, get an infection, and they have to kill the tank. So how do you know how much isocrisis is in a flask? You do these samples, and here's the scope that I use to do it with. Here's a close-up of it, and then if you look right underneath the scope, you'll see this what they call a hemocytometer, and that you might not be able to see it, particularly you people. I apologize for the ones with little laptops, or tablets or what have you, but there's these little circles in here are the actual phytoplankton, and you can see these squares, and so I count them, and record how much, and when it gets to a certain level, then we split the tanks. So that's me doing an experiment. Further on, I decided we ought to optimize how we're growing this isochrysis. And so I started, again, to the earlier question, I started experimenting with light levels. At first I thought the more the better. No, that's not true. You can burn them. I thought 24 hours a day would be perfect. No, they need to kind of like breathe in, breathe out. They actually call it respiratory, although it's not. It's photogenic respiratory. But they synthesize during the bright, and then they do the complicated thing where they free an electron for the photosynthesis in the dark. Here's the phytoplankton data that I take from that experiment. The second thing I work on is the kind of the main focus that I'm on now is coralline algae, totally different kind of algae. And the reason for it is I'm not especially interested in coralline algae. And when I tell people about it, they say coral. Oh, coral. Yeah, I get it. No, it's coralline. But coralline algae is part of a coral reef, for instance. Two different completely things. So, but at any rate, white abalone, which is a big thing at the marine lab, settle on coralline algae. And they have an increased likelihood of survival if they settle on coralline as opposed to some other artificial substrate. And there may be a chemical trigger from coralline called GABA. I don't know much about that, but that may stimulate settling. And if we were doing this where you guys had to answer questions, I would have asked here, how does a white abalone breed? So I'll let you think about that. I mean, there's this big shell locked to a, you know, to some stone or shell or the sea bottom. One of the problems with coralline is it grows really slowly, a few millimeter a year. So if you had to, you know, a size of an eraser, you know, say 10 millimeters, you know, if it grew 2 millimeters, that's hardly anything. And to try to grow, you know, 1,000 abalones on it, you know, you can see the problem. So that's the interest in coralline for me and for the marine lab. And here is some coralline. So you can see this kind of cloudy area here. This is coralline algae growing on a stone, piece of what they call cobble. And here it is in an aquarium tank. That colored part is all this is coralline algae. And here's some tanks. This is another volunteer out there, Rai. He's a really good guy. He graduated from not Sonoma Day School, Waldorf School. Anyway, he's actually teaching now. So a really good helper. And sometimes I think I work for him because he's got some really good ideas and a lot of energy. And we're both kind of shut down now because of the COVID thing. But at any rate, these are the tanks that we're doing some experiments with here with the various light levels. And you can see this where it says tank 4 right here, tank 3. They're fluorescent lights of different wavelengths of light. So say red light versus blue light, and to see the effect of growth on that. And in the next slide, you'll see the image you get of that light on the salt water. So this is the fluorescent lighting that reflects off of that seawater. And so I submitted that image to Optics and Photonics News. I knew they'd never be interested because there's some fabulous what they call image of the week. And so if you go back to June of 2018 on the OPN website, you'll see this image here. So that was pretty cool. So here is one of the tanks close up, and this is coralline algae here. So this is stuff that we've grown artificially or not in its natural environment in the ocean, in domesticated tanks here. And here's a coralline spore. And my thing is, let me move this a little bit. Yeah. So this was a picture that was taken at the marine lab by Dr. Jim Moore on the sample that we gave to him. So two really big projects at the marine lab are the white abalone restoration project and the urchinomics project. And again, each one of those is a talk in its own, and I'd cover those, but we'd be here till 3 this afternoon at least. But I give you these references, and I'll put links at the end of this talk, and links to the several abalone sites and several urchinomic sites. So here's a white abalone. I actually have one here. I don't know if you'll be able to see it. Most of you have seen an abalone shell. And here is a stone or piece of cobble with coral and algae on it. So a little show and tell. So here's, again, I'm not going to cover it, but these are the tanks that the white abalone are done in. And here is the tank setup. Way off to the left, you can see the tanks that I use, but they took out all the main tanks and put in this urchinomics setup. So some of the experiments, I think this was an earlier question that I'm doing now currently is I've asked people what, various things about coralline since we want to grow it and better. What's ideal? What's the best pH level? What's the best flow level? What's the best, should we use what they call grazers? In other words, other things to keep competing growth down. All these various things that affect the growth rate. And they say, well, what species are you using? And I had no idea. So I asked around at the lab and they had no idea. And it's a easy question, it's a difficult answer. And it's not because they don't know, it's because it's difficult to know. Because it has to be done with DNA sequencing. And I've actually done that now. I linked up from the lab with a guy at the University of North Carolina, Dr. Paul Gabrielson, and he's done some DNA samples on some coralline algae that I have and identified them. And also at the, let's see, what is it called? The Exploratorium in San Francisco. The professor there is doing some testing for us. And, but if we could do it with Raman, which is another thing, it would take quite a while to do, but it's a thing that I work on filters for at my day job. And Raman, you could just shine a light on it and it would give you a signature that tells you whether or not, well, it would tell you what the signature of that material was. If you can then further that signature to tell you that it's this species versus that species, you could do that immediately. So it'd be really handy and really inexpensive to do it. So that's one of the things I'm working on. It's similar technology to some of the spectrophotometry stuff, and the main component of Raman spectroscopy is optical filters that we grow at 2.6. So it's kind of a natural way to go over there. So another experiment we're working on is there's definitely a seasonality associated with white abalone, meaning in March or so, the abalone reproduce. And so I'll give you the answer to the question I asked earlier. How do abalone spawn? The way they do it is they receive some chemical trigger, and it might be light sensitive, or it might be something from this coralline algae that triggers the female to what they call broadcast spawn. So the female just releases all these eggs. I mean, they can be thousands, they can be tens of thousands, and in one extraordinary case, over 1 million eggs. And then that triggers the male to release sperm. And so the problem for white abalone is even though there's 4,000 or 5,000 of them, maybe more, maybe less, that are still out there in the wild, they're what they call functionally or practically extinct. Because if they're more than 4 or 5 meters apart, the sperm and eggs will never meet, and so there's no reproduction. So another thing I'm working on is conductivity, and I found this by accident. So can I affect the conductivity of a path in seawater based on the color and the intensity of the light that I shine on it? And all these are mostly on hold due to the COVID. So I haven't been out to the marine lab other than like this Zoom since March. So here's one of the setups that's in that little trailer that I showed you about that's measuring conductivity of the algae. Here's another one showing light levels that's using a programmable light fixture. So I can have it shut on and shut off on a 24-hour cycle. I can say do 14 and 8 or 12 and 12 or whatever I want to do on that. Here's a little way to do that. DNA sequencing using Neuramon. And here's the links that I mentioned to you that hopefully those will be available to you. If not, Milo can get them to you. But these ones here, you can pretty much just go to YouTube and Google or request or search for white abalone, UC Davis, or Cristinacalino. Any of those probably would get it for you. Or there's a longer one on endangered white abalone. So all those things would be a much better presentation that I could give you right here. But the other thing, here's a couple links to Urchinomics. This first one is the Urchinomics website. And it's like about a 4-minute video. And this is a really good one. It's a documentary sort of thing, quite a bit longer. And here's another thing. I don't have Instagram, but I asked out at the lab for some photos, and they referenced me to one of the aquatics resources group technicians out there, Sam Briggs, really excellent photographer. And so if you look up this Instagram site, I haven't been there, but I think you'll find some really, really interesting pictures. And if there was one thing you were going to watch and you have Netflix to get the flavor or the feel of what marine science, marine biology, the attraction of marine the Bodega Marine Lab is, watch this film. It has nothing to do with the Bodega Marine Lab, but watch this thing called My Octopus Teacher by Craig Foster on Netflix. Really excellent. So we're to the second Q&A.
Wonderful. Thank you so much, Rad. Students, while you're typing your additional questions on sort of the new topic of the Bodega Bay Marine Lab, I thought I'd just ask, what are the goals? How many abalones are you hoping to repopulate the waters with? And are you specifically focusing on any geographic areas like the Sonoma Coast or the Mendocino Coast?
Really, really great questions. It's a series of questions, and I'll try to answer them. In terms of the geography, the white abalone is mostly from Santa Barbara south down into Mexico. And it's almost extinct because of overfishing and because of a thing called withering foot disease or withering disease. And that disease was isolated at the Bodega Marine Lab. Dr. Jim Moore was key in doing that. So because of that work, the Bodega Marine Lab is one of a few along the coast and not many in the world where you can legally grow or harvest white abalone. It's an endangered species. It's the first endangered species mollusk on the endangered species list. So Southern California has warmer water and Northern California has warmer water. And because it's warming, there was a big debate about where to outplace the successful growth, down in Santa Barbara or up, more here near Bodega Bay. The decision was made to outplant it in Southern California. They've been trying to get abalone to reproduce in the wild or in captivity for, I don't know the number, I'm going to say 6 or 7 years. And maybe a little longer. The first years weren't successful. They eventually were able to get a few to grow, and then those ones would become second year, and then they got up to where they were doing maybe thousands. So the problem is, how many larvae do you get? Again, if it's done in captivity, you can get tens of thousands. But of those larvae, they'll settle if they're not on coralline, if they're on some other substrate, maybe 10% of them. So you're down to maybe thousands. Of those, how many will survive, become juveniles? Maybe again, 10%. So you can go from a lot to not too many in a hurry. And so I think they're successful now at thousands. This year was almost a disaster in the sense that the time when they reproduce is in the spring, March area, and there was very little successful spawning until this one, I forget the number, they actually have the number of it, and I knew it for a while, but this one female laid literally a million eggs. So it was like this disaster year turned into a bonanza year. And so the first year, I think last year, I could be wrong on this, the first year that they actually outplanted was also a disaster in the sense that they put them out in these little cages, and the first time they went for a dive to check on them, it's not publicized where they are and all that, just for obvious reasons. And when they went out there to look, they found that octopuses had been able to breach the cages. So there's all these little abalone shells laying around that, yeah, it was a bad outing. This time I think it'll be much better. So does that answer your question there?
Yes, thank you. So we have some student questions. The first one is from Kari, and she asked, did you ever think that you would get into marine life related science before you got this job? And did you already have an interest in it, or did you just happen across it?
That's also a good question. It's also easy question, hard answer. I knew about the Marine Lab, and I'd been to an open house like 10 years ago, and I found it interesting. And they showed the experiments, and at the time they were trying to do try growing lobsters on the West Coast, and there was a big salmon project, and I found it really interesting. And so I was aware of it, but I just assumed those things happened every year and didn't pay too much attention. But it turns out they only happen like every 10 years. So here's a heads up for any of you that might even remotely be interested. It's a Sonoma County thing, just like the Luther Burbank, if you're into growth sorts of things. But and they don't happen often. So when they do, be aware of it and try to, or I would recommend you try to attend. So I was interested, and then I went to this last one a few years ago, and was really interested. I went into that fluorescence lab that you saw there, and saw that they were using fluorescence scopes similar to what I used. They were using lasers. I talked to Dr. Gary Cheer. He's the whatever you'd call him, the acting director. He's the head dude out there. Really interesting guy, really smart guy, and was really interested in what we were doing. So I wouldn't say we established a relationship or anything, but, it was a good conversation. And so, it's getting senior in my career, and I was looking for maybe when I retire to have a soft bounce. And so I got interested. I went out one time and talked to the aquatics resources manager out there. They have a volunteer program, and Carl Menard, great guy, and he was interested in what I could do and what he could do. And so, so again, I knew very little, almost nothing about it. And, but they have these lectures. Again, they're not open to the public now, but, and I wouldn't recommend them unless you're pretty well down the road in marine science, but the graduate students report on their projects, and they're actually on Wednesdays at 1 o'clock. So now they're on Zoom like everything else. So, but I got interested in those and I attended them live. When I was out there, I could see the lab and see all the stuff that was happening. And then when they would talk about that stuff, it became pretty interesting to me. But to listen to one of those lectures now, I mean, when I first looked at the series of lectures, there wasn't a single one that I was interested in enough to go out to the lab and listen to. But after I'd been there a couple of years doing the volunteer work and hearing the jargon and knowing the people, I mean, I found them really, really interesting. Maybe one, maybe two is not interesting, and the rest of them are either interesting or really, I mean, like fascinating. So there was one on photography. There was one on oceanic sounds, you know, just, yeah, really interesting stuff. So that's how I got interested.
That's neat. Thank you. So I have similar questions from Sophia and Aaliyah, so I'm going to combine them. What do the water probes measure, and how are the water probes and other instruments made? Are they created using specific materials that can survive in the elements? How long do the devices last due to the harshness of the salt water?
Also really great questions. You know, at the time, when I first started, I was just helping out. So I'd take these probes and stick them in the water and write down on a piece of paper what the, say for instance, the acidity was. And then I'd give that to whoever was asking about it or interested, or one of the scientists, or Carl if he was, you know, curious about it. But I stripped this talk down because there was I just had too much to do, but I could give you a whole talk on the probes and what have you. If we maybe I could get back to that. I'll just tell you. So one of the things we measure is pH, so the acidity. And you've heard of ocean acidification, and I thought, well, that means that the water's acidic. It's not really acidic. What it is it's more acidic than it used to be. So if the water is really acidic, shells, you know, like oyster shells or abalone shells, they get thinner and weaker, and the animal has to spend most of its energy and activity just growing the shell, and it can't, you know, it ends up with a thin shell and could die, you know, in the extreme. So we measure the ocean acidity. We measure a thing called percent oxygen. So that's the amount of oxygen that's actually in the water, not the HO2, but the dissolved oxygen in the water. There's a special meter for that. And then there's an even more interesting to them, to the technicians, is the total dissolved gas. And that has to play with, you saw me measuring it out there at the clarifier. That's where the first place where it enters the marine lab, other than the actual entrance, the pipes under the ocean. And then I measure it also at the exit point, you know, the last place before it goes back into the ocean. And what they're interested in is that it'll show up things like pumping defects. Like if what'll happen is there's little screens, and these little animals, you know, little tiny larvae get through the screens. You know, some of them are microscopic, but for sure millimeter size. And they go through these little grids that they can get in there. And then they just stay in there for years, and they grow up into mussels or any other kind of marine life. And they can eventually clog that pumping system. And one of the signs of that is total dissolved gas. Another thing is there's aquaria that are available, you know, that are for the public, you know, so when you go to a lecture there, you'll see these big aquaria, which is also almost worth it for a trip to the marine lab. But, and there's some deep fish in there, and some of them, they have these kind of bulgy eyes. And the bulgy eyes can be to a fight with another fish, or it could be due to an injury, or it could be due to too much gas, too much total dissolved gas. So if I get a high reading, I report that, and they'll track it down. Another thing we read is the light level. So what's the percentage of light is. Then I read the temperature a couple of ways. So that's the main things that I read with those probes. The probes are made by outside companies. Because of the tight budget, I've actually repaired some of the probes, but some of them I don't want to mess with, and send them back to the company that did do it. Different ones are have a different lifetime. The ones I like the best are this company called YSI. I've never had one fail. They're always good. Some of them are a little bit obsolete because they've been around so long. But other ones, one of the ones, they don't make a total dissolved gas meter. So if they did, I would buy it or have the Marine Lab buy it. But another one to do this total dissolved gas is a really interesting company. It's a company of one in Idaho, if you can believe it or not, Sandpoint, Idaho. And I met the guy, and I think we might be his only customer at this point, but he makes a good meter, and I've learned a lot about it and what have you. So yeah, I've done some repairs. I've done some calibration. That's the main thing I do as well. I calibrate it against standards, and then I calibrate it against the instruments that the Marine Lab uses. They do an official, like ocean acidification measurement for that they have to report because they're environmentally protected, or they have a license, and you have to report the water that you're dumping back into the ocean, and so they do that separately, but I calibrate my stuff against it.
Thank you. We have two more questions. One is from Stefan, and he asks, what man-made problems contribute into making coralline practically extinct? And I'd like to add a little portion to this question. How do you think that climate change is affecting the work that you're doing, and or what importance does the work that you're doing have in combating climate change?
Yeah, another great question. So climate change shows up in a couple of ways, lots of ways, but the main one is this thing called ocean acidification. It can also affect things like red tide and just the amount of oxygen that's contained in the water. But regarding the ocean acidification, it selectively affects species, and one of them is what they call sea stars. Sea stars are, people might call them starfish, and they're a natural predator to these urchins. As I was mentioning, the urchinomic thing. The urchins, there's two main types. There's the big ones, the red ones that are harvested and used for uni, for sushi, and a big export to Japan. But there are these small purple ones that are all over the place. And because of ocean acidification, the otter population is, man searched down otter. There are very few left. And also the acidification has affected these starfish or sea stars, and it's decimated the population. So these purple urchins are going crazy. They're taking over the bottom of the ocean, and they wipe out the kelp. They wipe out these eelgrass, and that's the food for abalone and other marine creatures. So the answer, I guess, one answer is climate change affects acidification. Acidification affects species selection, which affects which species survive, and kelp, et cetera, et cetera. So.
Thank you. And we'll go ahead and wrap up with this one last question from Kari. She's referencing your mentioning of the one abalone who laid 1 million eggs. And she said, do you know what caused her to lay such an extraordinary amount of eggs?
I don't. That's a really good question, and I'm going to ask next time I'm out with the people that know about abalone. I don't do a lot of work directly with the white abalone, other than to try to supply the coralline algae to them. I know about some of it just because of conversations and some of these lectures that are given at times. But that's a really good question. I don't have the slightest answer to it. You know what I mean? I don't know what caused that one to do. I don't know if they know, but I'll certainly ask. And now I'm curious.
Thank you so much for your presentation today and taking the time to speak with students and us, and people will be enjoying the videos for indefinitely.
Thanks for having me.
Yes, thank you, Rad.